I will also open. Wait. Let me share the screen so that I can explain properly. Can you see this?
Yes, sir. Yes, sir.
Yes, sir.
This is the file which I have shared, right? Thermophysical properties of refrigerants. Is this the same one?
Yes, sir.
No.
Yes,
No.
yes.
2009 ASHRAE handbook.
Yes.
Yes, sir.
Okay. So here you can see on the very first page about different refrigerants. This part we have not seen, so I have to cover it first. Now the practical session which we are using over here, executing over here, the refrigerant is R11. R11 है ही नहीं इसमें. We are starting from R12. Then how we can use this? 717 ammonia. Methane series, why they have not given R11? Okay, I will share another file. Fine. So when you click on that, you will be directly forwarded to a table. If you look at it, it seems very similar to your steam table. So here temperature base, here pressure base, and then you can see liquid and vapor enthalpy, liquid and vapor entropy, similarly liquid and vapor CP, specific heat, and then further parts like viscosity, thermal conductivity, blah, blah, blah. Our interest is mainly towards the enthalpy part, because we have seen in our theory lecture that it would be the function of the enthalpies as such for the vapor compression cycle, the simple one. And compressor work is like, let's say 1 to 2 is compressor, 2 to 3 is condenser heat rejection, then 3 to 4 is the expansion, and 4 to 1 is the evaporator. Then 1 to 2 is compressor, so H2 minus H1. Do you agree? And
Yes, sir.
the evaporator section or the evaporation effect or refrigeration effect, whatever you call it, is between 4 to 1. So it will be H1 minus H4. Do you agree?
Yes, sir.
So on a chart, what we have to find out, or through the table, whatever you, the way you find it comfortable, finally our job is to find out these enthalpy values. So for that, it is given like the temperature and the pressure. So here we will be focusing on either the liquid part or the vapor part, depending on the case. If it is a liquid part, we will take liquid enthalpy value. If it is a vapor part, we will take vapor enthalpy value. But here, what if the state is not a saturated one? You can see it is very similar to the steam table. So temperature and pressure. If I know the pressure, I can find out temperature. If I know the temperature, I can find out the pressure. But these are the values related to the saturation. Do you agree? Steam table to yaad hoga na?
Yes, sir.
Right? So what if it would be something different? Let's say it is a subcooled version. Then what to do? How to find out? So again, theoretical formula. If it is superheated, then what to do? So again, formula. So instead of that, what we find on the next page over here, you can see for different pressure temperature range. Yeah, here there is a chart. And this chart is a slightly different version. I had not covered it in theory, but I am getting you some acquaintance with this. Here, the x-axis is enthalpy directly. Okay. And your y-axis is pressure. So this is called pH, pressure enthalpy chart. So the moment I locate the point over here on this pH chart, let's say somewhere over here, for example, then you directly take the x coordinate and that is your enthalpy. So how to locate this, that I will teach you afterwards. But just get the glimpse that this is a type of chart which will directly give you enthalpy. This is a kind of a modified version of the conventional chart. The conventional means PV chart. You know PV very well. You know TS very well, temperature entropy. But my job is to find out enthalpy, neither volume or pressure or temperature or anything. Rather, intersection of that pressure, temperature, whatever it is. The final objective is to find out enthalpy. Do you agree? Because we have to find out H2 minus H1 and H1
Yes.
minus H4. So basic job, final aim is to find out the enthalpy. So why not to take enthalpy itself as one of the axes? Correct, either X or Y. So we convert the entire chart as P and H. So now again, as similar to your TS chart, you will see this dome. Correct. So here left side is my liquid part. Inside the dome is a two-phase part, and over here is the vapor. So even if it is a superheated vapor, I can find out the state. Let's say somewhere over here. I will directly take the projection on the x-axis and directly read the enthalpy value. So now here your skill entirely gets concentrated on how accurately you get the point and accordingly the enthalpy. We will be solving the numericals also in our theory lecture. So that is not a problem. At 3 o'clock only we have lecture, right? Today?
Yes, sir.
So over there I will teach this part, obviously in full depth. But this is in the lab session just as the kind of exposure. Here you can read CP. So this is a critical point. On the left hand side, this is saturated liquid line. You can read over here also. This is saturated liquid. And here it is saturated vapor. Very similar to our TS interpretation. Over there also there is a dome. Inside the dome, two phase. The dryness fraction. Here you can see the dryness fraction 0.1, 0.2, 0.3, 0.4, x equal to, and up to 0.9 and 1. So this is my saturated vapor. Okay. Any problem in the interpretation of this? बाकी के lines क्या है?
No,
I
sir.
will teach you. In the theory lecture, I will cover this first and then we will go for the lab calculations. Today, I will just give you the exposure towards what is the experiment and how the values are taken. Calculation part we will do after the theory lecture gets over. Fine. Okay. So here, as similar to the TS chart, this is related to the dryness fraction. You know, x-axis, y-axis is the pressure and x-axis is the enthalpy. Okay. Then there are different temperature lines. This you can see over here. T is equal to 60 degree, 50 degree, 40 degree, means minus, then 0, and then positive 10, 20, 30. So what I will be finding is always the pressure and the temperature intersection. That will give me directly the state whether it is a subcooled or superheated or whatever it is. Okay. And then accordingly, the moment I trace it, take the projection on the x-axis, I will directly read the enthalpy value. So this will avoid any thermodynamic equations and calculations by substituting in the same and etc. etc. I will say that condenser pressure is some x value and the temperature is this much. Okay. And then you will find out if it is falling on the saturated part, then naturally it is directly phase change. If it is on the left hand side of the saturation, so that is subcooled. That means here, let's say intersection is over here. If you find it over here, so that is a subcooled part. Okay. If it is falling somewhere directly over here, then it is naturally a saturated version. If it is falling over here, saturated vapor. If it is falling over here, let's say superheated. As the same as what we have used with help of the steam table. So I hope you recollect the steam table. So any difficulty to anyone?
No, sir.
This is you are going to use for solving your numericals in theory paper and in the lab also. So this chart has to be very much crystal clear in your mind. If you have any difficulty, you can ask. Anyone from the class? Okay, fine. So this is how we are going to use this chart. Now, related to the experiment, I will tell you. Sorry. Now, let us first see this video. Can you see the screen?
Yes, sir.
Yes, sir.
Okay, let me make it full screen and we will start with the video.
Welcome to Academic Gain Tutorials. In this video, we will learn
Can
about
you
the
hear?
vapor compression refrigeration system,
Yes, sir.
with
Yes, sir.
its different parts
Okay.
and functions. So, let's get into the topic. We know that refrigeration is the process of lowering the temperature by removing unwanted heat from a selected object, substance, or an enclosed space and transferring this heat to another object, substance, or space. Now, from the name vapor compression refrigeration system, we can understand that in this process we will compress a vapor refrigerant inside the system to obtain the refrigeration or cooling. If we are going to compress vapor in this system of refrigeration, then obviously we will need a compressor for this job. So, the process of compressing the vapor refrigerant inside the system using a compressor to obtain the refrigeration or cooling is called vapor compression refrigeration system. Now, let's look into the major parts and components and basic working procedure of the vapor compression refrigeration system. So, here we have a compressor, after that there is a condenser, then there is an expansion valve or throttle valve, or we can simply call it a valve, and finally, there is an evaporator. So these four major components together construct the vapor compression refrigeration system. All these components are connected together using these connecting pipes, thus a closed-loop system is formed, and the refrigerant for this vapor compression refrigeration system will flow through all these components and pipes in the system. Now, let's see how these components work. Throughout the whole process, our main purpose will be to ensure that continuously cooling effect or refrigeration effect is obtained in this evaporator. We all know that this evaporator is the component where the refrigeration or cooling actually takes place. This evaporator is placed on the region where we need cooling, and then the evaporator absorbs all the heat of that region and passes those heat to the cold refrigerant passing through the evaporator coils. Thus the surrounding environment cools down. So, let's see how this process works. First of all, this compressor starts working. The job of the compressor is to pressurize or compress the vapor refrigerant inside this compressor chamber. Here, in vapor compression refrigeration system, we commonly use either ammonia or freon as a heat-carrying medium throughout the whole procedure. Now, we know that if pressure increases, it also increases the temperature. So, when this vapor refrigerant is compressed inside the compressor chamber by squeezing the vapor very tightly together, it will heat up. After that, this high pressure and high temperature vapor refrigerant will leave the compressor and will enter into the condenser through this connected pipe. Here, we have a condenser. When high temperature, high pressure vapor refrigerant enters this cold condenser, then the condenser absorbs the heat from the vapor refrigerant and completely converts it into liquid. This condenser can be water cooled, air cooled, or cooled by any other substance from an external source, which will liberate the latent heat of this vapor coming into the condenser, and thus condensing keeps happening. So, in easier words, condenser changes the incoming high temperature, high pressure vapor refrigerant into liquid state by changing its phase. Here we had vapor coming in, and now we have liquid refrigerant going out, so the phase is changed. Now this high pressure, high temperature liquid refrigerant will leave the condenser and pass through this expansion valve or throttle valve using this connected pipe. Now, this high pressure liquid refrigerant.
Just a moment. Am I audible?
Yes, sir. Yes, sir.
Yeah, here this is high pressure, high temperature. No, this is high pressure, low temperature because the heat is rejected. It's a slight mistake over there. This is high pressure, high temperature vapor. When you reject the heat and the phase change takes place, so naturally temperature reduces and vapor gets converted into liquid. So there is a slight mistake over here. Okay, this is a condenser. It has to reject the heat. That is why phase change takes place. So this would be
Yes, sir.
at a slightly lower temperature. What the person is saying is like the pressure is constant and it is just a phase change. So naturally, as the phase change associated with the constant temperature, that is why the person is saying high temperature. But this is not a high temperature as such. There will be slight cooling also. In practical, in reality, it is let's say superheated vapor. I will say over here high pressure, high temperature means superheated vapor. Then initial rejection, it comes to the saturated vapor, then further rejection, it goes to saturated liquid. Okay, and then even further slight reduction as a subcooled liquid. So there is a reduced temperature. What the person of this, the creator of this video is describing is simple phase change, as she said. So that is why she is saying for high pressure and high temperature only. High pressure, high temperature vapor to high pressure, high temperature liquid is equal to only phase change. Do you agree?
Yes, sir.
Yes, sir. That is not the practical reality. She is explaining only the theoretical part, so that's why she is saying. But in reality, practical reality, we convert the phase change. That there is slight part on the superheated section also, and slight heat rejection on the subcooled section also. So we will discuss about this more in our theory lecture. Okay, fine.
Refrigerant coming from the condenser will be expanded inside this expansion valve. We know that when expansion occurs, the pressure between the molecules decreases considerably, thus the temperature falls. So, this high-pressure liquid refrigerant will be expanded into low-pressure, low-temperature liquid refrigerant. In practical use, at this point we do not get only liquid refrigerant, but here we actually obtain a mixture of low-pressure, low-temperature liquid and vapor refrigerant. Thus, here we get a mixture of very cold, chilled, low-temperature liquid and vapor refrigerant coming out of the expansion valve. Then, this liquid and vapor mixed refrigerant will be passed over to the evaporator. We all know that the main cooling effect or refrigeration effect always occurs in the evaporator. So, when this low pressure, very cold, chilled, low temperature liquid refrigerant will enter the evaporator coils, it will absorb all the heat present in the surface of the evaporator coils. By absorbing all the heat from the surrounding region of the evaporator coils, this cold chilled liquid refrigerant will completely turn into low pressure vapor refrigerant inside these coils, and the surrounding region of the evaporator will become cold by losing the heat to this liquid. Thus the cooling effect or refrigeration effect has occurred in the evaporator. After that, this low pressure vapor refrigerant will leave the evaporator and enter into this compressor through this connected pipe. Now, this low pressure vapor refrigerant coming to the condenser will be again compressed inside the compressor chamber and converted to high pressure high temperature vapor. Then again this high pressure high temperature vapor will be passed to this condenser where it will change phase and will be converted to liquid. Then it is passed to the expansion valve, the evaporator and again to the compressor. So the cycle keeps repeating over and over again, and refrigeration or cooling is obtained continuously in the evaporator region throughout the whole process. So, this is how vapor compression refrigeration system works. Thank you for watching this video. If this video was helpful, subscribe to my channel Academic Game Tutorials for more.
Fine. Any doubt to anyone?
No, sir.
Okay, I will share the link of
Sir,
this
how do we
video.
get the vapor outside, coming out of the
Sorry?
expansion valve?
Sorry.
So how do we get vapor coming, liquid plus vapor out for the output of expansion valve?
That I will explain with the help of that pH chart only
Okay.
in the theory lecture. Okay. So any doubt in this cycle? How the cycle is getting executed?
No, sir.
Okay. So this is the first, what I can say, theory part as such. So I will show you now our system. This is the schematic part. Now we are converting this theoretical part into the actual theory. So the title of our, what I can say, experiment is the water cooler. So the basic part is to cool the water. So our evaporator is nothing but, let's say, some kind of vessel filled with water. Then the coils, refrigerant coils are passed through it, that container which is having the water. So water will come in, water will go out with some mass flow rate. Okay. And the refrigerant will come in, refrigerant will go out with some mass flow rate, and in between there will be the heat exchange. So I will here share the screen for our experiment part. Can you see this?
Yes, sir.
Good. So trial on a water cooler. So I will show you the same set up over here. So you can see, or should I reduce slightly? Huh. This thing, I think better. Yeah, fine. So here is my compressor. Okay. So let's say saturated vapor over there, you compress it. It goes to somewhat superheated part. It goes over here. In the condenser, it will be rejecting the heat. So there is a fan to reject it to the atmosphere. Okay. It comes back to the liquid state again by rejecting the heat and obviously phase change. It comes to the liquid part. Then it comes over here. This is my expansion device. So high pressure, but liquid part gets expanded. So it becomes low pressure and liquid plus vapor. How it happens, I will explain in the theory lecture at 3 o'clock. Okay. And then this comes into the, sorry, this is our evaporator part, correct? So it comes over here, this water in, water out. So water in will be at, let's say, room temperature, 27-degree, 30-degree, whatever it is. Okay. Then this refrigerant will absorb the heat from this water. It will be parallel flow, counter flow, all those things theory come into picture. I hope you are clear with that. You are able to recollect it. Same 5 heat transfer course. Okay. So let's say in inner pipe there is water, outer pipe there is, in the annulus there is a refrigerant, or vice versa, whatever it is. And accordingly there will be counter flow or parallel flow arrangement that we will discuss afterwards. Okay. And this water will reject the heat. The refrigerant will absorb the heat. So water will get cooled. Refrigerant will absorb the heat. It becomes hot and finally completes the cycle and enters into the compressor. So this is how the entire structure, entire cycle gets complete. For the compressor, we have an energy meter with the help of which we will be taking the reading for the compressor power input. So basically work H2 minus H1. Fan is a like a negligible one, so we can neglect it as such. Okay, compressor power is 1.5 HP. Fan power is 1 by 8 HP. Fractionally, very negligible part. Okay, and oh, refrigerant is R12 only, so you can use our chart. I thought it is R11. Fine, so we can use R12 chart. Mm, what else? So here the water flow, or let's say water substance, is my evaporative load. So let's say it is getting entered at some particular temperature, room temperature. So how much I would achieve as the cooling effect? So naturally it is like a sensible cooling. Do you agree? Water is getting cooled, so it is sensible cooling.
Yes, sir.
Simple. And for the refrigerant part, it is a latent one. Because as explained in that earlier video, it is a liquid plus vapor mixture which is absorbing the heat from the water. Water is rejecting is the sensible heat, and what the refrigerant is absorbing is the latent heat. Do you agree?
Yes, sir.
So that is why for the refrigerant the phase is getting changed. For the water there is no question of any phase change. It is rejecting the heat as a sensible one. So let us assume that let's take some random value. So water is entering at 30 degrees Celsius, getting cooled at let's say 15 degrees Celsius. So this 30 to 15 is a sensible part. And sensible part means m dot into Cp into delta T. Cp of water is constant. Delta T is the final effect depending on the m dot. We change the m dot. Accordingly, delta T will change because your inlet is constant. So higher the m dot, delta T will be lower. Lower the m dot, delta T will be higher. Do you agree? M dot Cp delta T. So is the water side clear?
Yes, sir.
Fine. Now we assume for the first law of thermodynamics to be valid, 100% applicable. Correct? So whatever is the heat rejected by the water in bracket sensible, जो अभी discuss किया m dot Cp delta T is equal to m dot into delta H, or I should say HFG. for the refrigerant. Do you agree? First law. Heat rejected by the water is equal to heat absorbed by the refrigerant.
Yes, sir.
So heat absorbed by the refrigerant will be again the function of m dot of the refrigerant and HFG. So whatever is the pressure, its corresponding saturated temperature, and accordingly the HFG. The very same way, if I say water, 1 atmosphere, then you will find out from the steam table 1 atmosphere means 2257 kg per kg, HFG. How do you find out? You read the steam table. So same logic, refrigerant table. Instead of steam means water, H2O, it is another kind of working substance, any refrigerant. So the moment you come to know about the evaporator pressure, or let's say even working temperature, then we will find out its corresponding saturation values for the enthalpy at liquid and enthalpy of vapor phases. And difference between that will be our HFG. Do you agree? Let's say I give you example, random value. Let's say -5 degrees Celsius. So from the table ASHRAE chart, whatever I just shared with you earlier on the GVC, कितना बोला मैंने, -10 degree, whatever it is. Okay, तो -10 का you will find out for liquid enthalpy, vapor enthalpy. So that will give me HFG. Correct? If of course it only involves for the phase change part. अगर उसके ऊपर कुछ होगा superheated and subcooled वगैरह वगैरह, that is the extra part. But in our experiment we are assuming that it is related to only the sensible part, sorry, latent part, phase change. Okay, so that is how we make the first law of thermodynamics getting valid over here, that whatever is the sensible heat rejection by the water is as the same as the latent heat absorbed by the refrigerant. Do you agree?
Yes, sir.
Okay, so this is how we will move ahead. You can read this at your home, and this is what I told. Q absorbed is equal to the Q which is rejected by water. MCP delta T is for water, and that is what is Q absorbed. So I will not calculate practically the heat absorbed by the refrigerant, but I am calculating it indirectly, directly in the sense of refrigerant. What I am doing is indirectly, that means in the sense of water. Because we are assuming the first law of thermodynamics to be valid, and nothing wrong in this assumption. So whatever is the heat rejected by the water is as same as heat absorbed by the refrigerant. Any problem?
No, sir.
After this, we will calculate heat absorbed divided by work done. How you will find the work done? Compressor work. So energy meter. That will be
H1
directly.
H2.
You can get the directly energy meter reading.
Okay.
So this covers about my practical part. Okay, so I will have a practical COP. Practical heat absorbed, which is equal to MCP delta T of water. Practical heat rejected by water is equal to practical heat absorbed by the refrigerant, correct? So this will be related to the water part, MCP delta T, which you can measure. You can measure m dot, Cp is constant, you can measure delta T. Simple thermometers, correct? So this numerator part is done. Now the denominator, there is an energy meter which is supplying the power to the compressor. We are of course neglecting this fan because 1.5 HP के comparison में 0.125 HP is not even, means lesser than 10%. So I can neglect it. Fine. Now I get the work done with the help of the energy meter readings. So this is how I calculate the COP practical. Up to this part, any doubt to anyone? How we are calculating?
No, sir.
Fine. Now I want to plot the same cycle on the pH chart. Here the description I have given with respect to TS chart because pH I have not yet introduced. So let's say over here. Now if I want to plot this, what do I know is the condenser pressure over here and the evaporator pressure over here. But I do not have the temperature readings. I will be measuring the temperatures of the water part, not not the refrigerant part. Okay, in our setup, I'm talking only about our setup. So there is no scope of measuring the temperature of the refrigerant circuit. What we are measuring is only water temperature in and water temperature out. So then what should I do? So what we do in this experiment is we assume two different cases. Let's see them simultaneously. So one is the dry saturated compression start and the other is dry saturated compression end. Do you agree? One is dry saturated and here two is dry saturated. Okay. Rest of the thing is same. 3 to 4 same. Pressure same, temperature same, everything same. Only the compression process is change. Any doubt?
No, sir.
Okay. Now naturally over here the COP would be different because your refrigeration effect is also different and compressor work is also different. Here refrigeration effect is smaller, compressor work is small. So I will get one COP from this assumption. I will call this as COP dry saturated. One more COP from this assumption. I will call this as COP wet compression process. And then I will compare this COP practically calculated and predict what kind of process, compression process, is actually getting executed inside the circuit. In other words, let us take some value. Let's say this value, dry saturated compression, would be, let's say, 4. Okay. Then wet compression, naturally it is lesser. So let's say 2. Then if this value, practical value, comes out to be 3.5, then I will say that my compression process is somewhere between the wet and the dry. Do you agree?
Yes, sir.
Yes, sir.
Here it is 4, here it is 2, that means somewhere in between. So इसका मतलब है यहाँ से कहीं से start हो रही है. It is not reaching to the saturation point and not even here. Somewhere in between, maybe somewhere here, anywhere. So partially wet. Fine. If my practical COP value would be lesser than 2, let's say 1.5, then I will say my compression starts over here. Entire process is in wet zone. Do you agree?
Yes, sir.
And if my COP is greater than 4, let's say 5, then it is a superheated compression. इससे भी आगे. Do you agree?
Yes, sir.
Fine. So that is the objective of this particular experiment, to find out the process of compression taking place. I mean to say type of compression process taking place. So whether it is a complete wet, whether it is wet saturation or dry saturation or superheated one, whatever is the actual compression process taking place in the circuit cycle, that we will find out. So this is your experimental write-up. So our observation table is time required. I have to measure the m dot of the water. So let's say 1 liter of water. So I will give you these readings afterwards. Okay. So whatever, let's say what 50 seconds, 60 seconds, 70 seconds, whatever it is. Then the evaporator pressure, then the condenser pressure, then the water inlet temperature, which will be common, constant, because it is room temperature. Then the water outlet temperature. So this will be strong function of the mass flow rate. We discussed m dot into Cp, which is constant, into delta T. Out of this is also constant. So more the mass flow rate, lesser will be delta T. This temperature will be closer to TW1. Lower the mass flow rate, delta T would be higher. So TW2 will be away from TW1. Do you agree?
Yes, yes, sir.
Correct. If m dot is smaller, That means delta T is large. So TW1 minus TW2 is large. So TW2 is away from this. If my m dot is very large, that means delta T is very small. That means TW2 is closer to TW1. I hope you agree now.
Yes, sir.
And the last column is towards the time for the 10 revolutions of energy meter. So we will take the reading for 10. Why 10 revolutions? Because we have to take the average basically. Okay. So we will take this reading, convert it into corresponding watt or kilowatt reading directly. And since this is m dot into Cp delta T, mCp delta T hota to joule mil jata, joule or kilojoule. Since I am taking m dot, it is joule per second. So I will directly get kilowatt. So your mCp delta T as the numerator in kilowatt or watt, and denominator is your work, which is again watt or kilowatt. So accordingly, COP can be very easily found. Fine. Any doubt?
No, sir.
Okay. I will now show you one video about the actual experimental setup, not from VJTI, some other college. So here we will be having our result. What is our m dot? So let's say 1, 2, 3, 4. Then what is Q absorbed? We will find out about the deviation, increasing, decreasing, jo bhi hai. Okay, then work done again. Increasing, decreasing, constant, whatever it is. Then COP experimental with the help of these. And then COP from the graph for the dry saturated one and for the wet one. So here we need the chart. Graph matlab chart. Up to this part, COP experimental, what we need is the readings. Fine.
Yes, sir.
Any doubt to anyone in theory, whatever I just explained?
Sir, can you explain the table which was above, the one which took the values of TW and TW2 and pressure? Yeah. Sir, why those pressure values we are taking? Means to check that whether it is wet compression or dry compression, right?
Otherwise, how you will plot on pH chart?
No, I'm just asking that. Means okay, we have to plot on pH chart. Got it.
On pH chart, it is a pressure versus enthalpy. So pressure I have to know. Both for evaporator and the condenser. अगर वही पता नहीं होगा तो चार्ट पे प्लॉट कैसे करेंगे?
Sir, got it.
Okay.
Yes, sir.
Now I will close this. I will load that video. I will share the link also afterwards. No problem. To share the screen. Can you see the screen?
Yes, sir.
Yes, sir.
So I will make it a full screen. Here our setup is similar to this setup. I'm not saying exactly. This is much more sophisticated one. Our setup is donated by Queen Victoria 100 years ago. So that is a very old setup. And probably that is the reason it is still in working condition. Okay. So here, just I will show the similarity, how it is analogous to our work and how we take the readings basically, so that you will get the idea. The arrangement of the circuit is same, but in quite what I can say different manner done. I will show you the photos of our actual setup. I had taken it yesterday. So I will show you that also. So setup दिखने में सिर्फ अलग दिखेगा, circuit is same. Okay, so let us start. Is the audio clear?
Experimental setup for doing this refrigeration experiment. So let's familiarize the parts first. As you know, for a
So could you please increase the audio?
Huh?
So volume is very low, sir.
At my end it is full, you can see. Or should I share the link?
Yes, sir.
I think the video itself is having lower audio, poor audio quality.
It's
What
fine,
do
sir.
you
Play it
want?
then. Play it on screen only, sir. If the video has low
Because
audio
here I
quality.
have put it as full, and you can see this.
So can you hear it properly, like on your end?
Yeah, I'm using headphones, so that is why clear to me. If you want to bring the headphone, I will wait for 1 minute. Bring the headphones, that will make it clear.
Okay, sir.
Bring the headphones, I will wait for 1 minute. After that, we will start.
Sir, else can you share the link?
This is the link. Shared. Fine, should I start? Ready with headphones?
Yes, sir. Yes, sir.
Okay.
condenser, expansion device, and evaporator. So this is our compressor, this is the condenser, and this is the expansion device, and then it goes into the evaporator coil. So this evaporator coil is wound in the chiller. Not chiller, this is an insulated chiller in which we have kept 10.5 kilograms of water inside there. So this is our mass of water, and this is the sensor to measure the temperature of the water. So now let's do the experiment. The aim of the experiment is to find out the CO coefficient performance of the refrigeration apparatus. So we know that the coefficient of performance is determined by the formula refrigeration effect by work done. So how to calculate the refrigeration effect? It is by using the formula mCp delta T of this water. The mass of the water into specific heat of water at constant pressure into the temperature difference that is occurring in this experimentation, right? So what we need to do is let's switch on the main switch. So the compressor is started. Now we need to measure the temperature of water at first itself, because we need to measure the temperature before this refrigeration begins. So let us note the temperature readings by adjusting the knob to T5. So T5 is the temperature of water in the chiller. Now the process, as you know, it is the isentropic compression in the compressor, then isobaric condensation in the condenser, then the uh, isenthalpic expansion in the expansion device, and then isobaric um, evaporation in the evaporator. Now, the readings to be taken is, as we know, for mCp delta T, the refrigeration effect, we need to have two readings. So we have taken the reading of the temperature, we have taken the temperature indicator reading, and after 5 minutes, let us take the temperature reading again. So that is for the calculation of refrigeration effect. For the calculation of work done, we need to note down the energy meter reading. So here we can see the energy meter, and the energy meter constant is available. So by using this energy meter constant and the reading for the time taken for 5 revolutions, we will be getting the compressor work input. Right. So by this calculation refrigeration effect by work done, we get the actual COP, and the aim of the experiment is to compare this actual COP with that of the theoretical COP. For theoretical COP, we go for the pH chart, the pressure enthalpy diagram. We can plot this pressure enthalpy diagram using the suction pressure and discharge pressure. So the only two parameters to be measured for calculating the theoretical COP from the pH diagram is the two pressures, suction pressure and discharge pressure. You can see it here. So this shows the suction pressure and this shows the discharge pressure. So from these two pressure readings, we'll be able to plot the diagram. We'll be able to plot the graph with the pH diagram, right? And from that, by using the formula H1 minus H4 divided by H2 minus H1, the refrigeration effect by work done, we get the theoretical COP. So comparing these two, actual COP and theoretical COP, is the aim of our experiment. Thank you.
Yes, sir.
Okay.
Almost.
Any doubt?
No, sir, no doubt.
Okay. So here, as the video said, those who were not able to listen to the voice properly, I have shared the link. So are you now fine with that?
Yes, sir. Yes. Yes, sir.
Okay, fine. I will do one thing. I will delete this message and I will share all the links afterwards. It's not a big problem. Now, I will okay, the compressor which he had shown in the video is over here at the bottom. Okay, since it is 100 years old, it is very bulky one. Fine. So from condenser it goes, compressor it goes to the condenser. Okay, and after this heat rejection through the condenser, it comes to the throttle. Now this throttle is over here. In that particular video, what was shown is like a solenoid control valve. Our setup is 100 years old, so it's a simple copper capillary. So this is what is one type of expansion device. Nowadays, it is much more advanced, so you can use solenoid control valve and many other thermostatic expansion valve, many other things are there. In the next experiment, I will show you the thermostatic expansion valve. Okay, so compressor, then condenser, then this tube, what you see over here, chota sa, that is my expansion valve, and then it entirely goes into this black box, which is shown over there, water filled. So that is my evaporatory unit, or basically refrigerated section. Fine with this figure?
Yes, sir.
Now here what we make is there is a water inlet from this side. I will show you another figure. Water inlet from this side. Here there is a tap through which the inlet water comes like this. It goes into this black box. Okay. And then comes out from this pipe. So naturally it is a sensible heat rejection. Water temperature is reduced, which I can measure over here. Here also you can measure. Here also, anywhere you want, you can measure it. So that will be my room temperature as the inlet. So that is my TW1. And the exit temperature at here, anywhere you want, you can measure it. So that is my exit temperature, TW2. And over here, I will hold some measuring flask, 1 liter. Okay, one student will take the time reading with the stopwatch. So this way I can measure m dot 1 kg or 1 liter, one and the same for water, correct? Density is 1000. So 1 liter or 1 kg, and how much time to get it collected. So this is how I calculate m dot. Then TW1 at the inlet, that is the tap water, TW2 over here or anywhere across the length of the pipe as such. That is why it is insulated, so as to avoid any heat transfer further. So this is my outlet temperature, this is my inlet temperature. So my numerator part, m dot into Cp into delta T, is measured. Any doubt in this?
No, sir.
No,
No
sir.
doubts.
Okay. Now here you can see those coils, very similar to our what you call radiator. You can see automobile radiator, 4-wheeler. Okay, so that is acting as a condenser, and this is the motor for the fan, which is helpful for rejecting the heat from the refrigerant to the atmosphere. Fine. Any doubt? Even if you have any simple doubt, please ask and make it clear in the mind. Okay, one more feature. It looks like this from the front end. So high pressure, that is condenser, low pressure, that is evaporator. In our setup, these units, because it is 100 years old, the units for these pressures are in PSI, pound per square inch. As I said, gifted by Victoria, so it is in British units. Okay, nowadays whatever you measure is in bar or atmosphere, generally bar only. So here it is PSI, we have to convert it into SI units. Okay, so here you can see again the same thing, compressor, condenser. It's a very small capillary tube over here at this point. That is my throttle. Oh, sorry, here at this point. Okay, and then it goes into the black box, that is my evaporator. So currently the problem is that the water supply is not working. As you are aware that below the refrigeration lab, there is an IC engine lab, and IC engine lab and RAC lab, the water supply is common from that tank in the ground, underground rather. And that pump is not working because in last 1.5 years, there is no maintenance, no nothing. Never it was started. So I found out on Friday that it is not working. Otherwise, I could have shown you this thing live also. See, even though I start with the refrigerant circuit, water circuit is not going to start. Since the pump is not working, no water circulation is possible. So that is the only problem. Otherwise, this unit is properly working. If the pump starts working, I will show you live also this thing. Okay, so the setup which was described in the video and this one is one and the same. Circuit is same. There is a compressor as it is shown over there, compressor, और उनके वीडियो में इसके बाजू में ही कंडेंसर था. हमारे केस में ऊपर लगाया हुआ है. Nothing other way difference. Then they were using, I think, solenoid control expansion valve. Our is the old one, copper capillary. And then very similar to their box in which that water was stored. Here it is a water flowing. So m dot Cp delta T. What they were doing is like 10 kg of water, 10 liters of water stored in it. And you could see that the temperature starts falling down. 18, 17, 16, 15, 14, and like that. Right? Here, since the water is flowing, we will be measuring TW1, that is inlet, and TW2, that is exit. So m dot into Cp into delta T. Logic is same. Theirs is a stored one. Ours is a flowing one. And why we made it flowing? Because we will directly get the reading in watt or kilowatt, because it is time derivative. Okay. Now, next figure. Yeah. This is our compressor. This is that black box. ये सब अंग्रेजों के जमाने का है. And probably that is the reason it is still working.
Sir, where is the power meter, sir, for measuring power?
दिखाता हूँ. Wait. Fine. The close-up of the pressure gauges. So here you can see these are in PSI. Okay, you can see the condenser tubes again. Fine. This is our energy meter. So as you have seen in that video, it starts rotating and there is a red color mark on this disc. So whenever it, let's say, crosses this particular, what I can say, indicator, then I can directly take it as one circulation, one rotation. So how many number of rotations? And then into the energy meter constant. So that will give me directly watt or kilowatt, whatever is the reading. Here it is mentioned that it is kilowatt hour. Okay. So in the actual setup, in the actual scenario, offline mode, I used to put like 3 people for water flow measurement, 3 people for taking the stopwatch reading, 3 people for taking the energy meter reading, and 3 people for having the temperature readings. Inlet temperature anyways is constant, that is a tap water. Only the exit temperature of water, TW2, is to be noted down. This is how we execute the actual experiment. Fine with this? Any doubt to anyone? You can see over here, Chamberlain and Hockham, Birmingham. Everything is Victorian. Okay, so these are all our figures, our photos, actual photos of the setup. Fine. Any doubt to anyone for this total setup or how the experiment is conducted? I will try to see if the pump gets started, then I will show you a 5 minutes video of actual cooling. Probably next week or something like that. Fine. Any doubt to anyone? Theoretical aspect.
So where is the fan at condenser?
उसके पीछे. I will show you from other side. इधर है. इधर से fan है. The heat will be rejected. Means flow is in this direction. Air flow is in this direction. Front side. खिड़की के पास fan है ये पीछे से. This is motor for the fan.
Okay, sir.
And whatever is the flow of the refrigerant through these coils, it will reject from, let's say, left to right. If you stand in front of this, you will feel hot air.
Sir, if the pump is not working, sir, why don't we use the same method in the video, like storage method?
What is not working?
If the pump is not working for the flow of water, why don't we use the storage method, like they store the water and measure the temperature, right?
You can do it. Nothing wrong in that. whatever amount you will get, means the unit will be joules, means not watt but joules. Nothing wrong that, as I told. If I take m, that is total mass, I will get what you call joules or kilojoules. If I get m dot, I will get watt or kilowatt. Why we made this setup in such a way? Because energy meter is in watt. Otherwise, you convert energy meter into joules or kilojoule, of course.
Okay,
Nothing wrong, na? Basically, you are just taking the time derivative. Energy meter constant is known, so I can directly get the reading in watt or kilowatt. So for that purpose only we use the m dot part. Otherwise, you store it inside. It will be m. So how we designed it in this particular setup is like a heat exchanger, in which like one fluid inside the pipe, one fluid outside the pipe. Otherwise, use it as a storage one. If you recollect the video, first video shown, it was like a storage part and the evaporator coils dipped inside. Correct? Theoretical video, पहले जो दिखाया था.
yes, sir, right, sir.
Over there, it's a component, the cube box, whatever you call it, storage, and the evaporator coils passing through that. So heat rejected will be in joules or kilojoules, not watt or kilowatt. You take the time derivative, you get watt and kilowatt. Fine. I will see that it would work out, means the pump, because setup is absolutely fine. Setup को कोई problem नहीं.
Sir,
Yes.
what is P1 in this? Is it condenser pressure or evaporator pressure?
Compressor process काय सांगा? 1 to 2. What is 1? If compression starts at 1 and ends at 2,
Yes, sir.
what is 1? Evaporator or condenser?
Evaporator.
So that is evaporator pressure. 2 is condenser pressure.
Sir, the another photo, it was written high pressure and low pressure.
So high means condenser, na?
Yes, sir.
After compression only it becomes high pressure, na? Quite
Yes, sir.
simple.
So high pressure is P2 and then P1.
Huh.
Okay, sir.
After compression only it becomes high. Otherwise, how you will generate high pressure?
Yes, sir.
Okay. Any other doubt to any person? Howsoever silly it may be, but please ask. No doubt. Very good. So, should I move ahead?
Yes, sir.
Okay, fine. Now I will show you. I will share these photos also with you. I will show you now one more video. Why there are advertisements every time?
So use Brave.
Eh?
Brave browser. Sir.
Can you see the screen?
Yes, sir.
Okay. So this is another video. Similar setup, rather same setup. Theory is same.
We have studied in the class concepts of vapor compression refrigeration. This setup, the attempt to utilize the concepts which we are learning in the class. You know that vapor compression refrigeration is a very interesting kind of system found in all practical refrigeration parts.
So what we will be doing first is we will be locating the major components, the core components of the vapor compression refrigeration system. What are they? We know that it's the vapor compression refrigeration system, and the high refrigeration system is the compressor. So can you see the compressor over here? Look at this black small setup which you see over here. This is the compressor. This is a Kirloskar made hermetically sealed compressor which is found in small setups. Okay. So this is a compressor, and you know that this compressor is going to compress the refrigerant from the suction pressure, that is the evaporator pressure, up to the discharge pressure, which is the condenser pressure. So where is the condenser? So you see that the condenser, this is the system which is a low capacity system, and the condenser would be a air-cooled condenser. It won't be a water-cooled condenser as in the larger setup. So where is the air-cooled condenser? Look at this setup. You see over here that this is a condenser. There are some coils, and you see some fan. Fan is to increase the heat transfer coefficient. You know that primarily the heat transfer would be from convection, and by using the fan, we can enhance the heat transfer. So condenser, what does it do? Condenser, you know that the refrigerant will flow from the compressor to the condenser, and the condenser will reject the heat to the surrounding. After the condenser, the refrigerant will move into the expansion device. So look at this coil kind of thing, the copper coil kind of thing. This is the expansion device. This is the capillary tube which is found in the.
Our expansion device is similar to this. In the earlier video, what you have seen is the solenoid type of expansion device. Ours is like this, simple copper capillary. Okay.
Domestic refrigerators. So this expansion device would help us to reduce the pressure from the discharge pressure, that is the condenser pressure, up to the suction pressure, which is the evaporator pressure. So this is the expansion device. And then where does it go? Where does the refrigerant go? The refrigerant will go from this expansion device into the evaporator pipe. Look at this. This box which you see over here, this is the evaporator chamber. And in this evaporator chamber, there is water in it. The water will be cooled by the aid of the coils. Look at this. You see that there are some coils over here. These are the copper coils. And these copper coils are the coils where the refrigerant is circulated. And the refrigerant would extract the heat from the water and produce the refrigerating effect. So the refrigerant coil, in this case, is housed in this container. And this container, what actually happens in this container is that you reduce the temperature of the water. Now, by what temperature? What temperature the water? At what degrees the water temperature reduces? That would be crucial to find. So, in order to find experimentally the refrigerating effect, what we do is that we note down the temperature, initial temperature of the water. We note down the final temperature of the water, and we know that there is a known mass of water in this container. By knowing the known mass of water in this container, by knowing the specific heat of water, which is 4.187, and by knowing the temperature before starting the refrigeration and after starting the refrigeration, that upon the time of conducting the experiment, that is young Cp delta T of water, upon time of conduction of experiment, it will help us to determine the capacity of the system, that is the refrigerating effect of the system experimentally. So in this experiment, we can find the refrigerating effect by actually measuring the temperature of the water, initial temperature, final temperature. We must know the mass of the water, and we must know the time required for cooling this water. Okay, so that gives us the refrigerating effect experimentally. How do we find the compressor work experimentally? Because we know that performance is the coefficient of performance is the ratio of refrigerating effect to the compressor work. So how do we find the compressor work or power consumed by the compressor experimentally? So look at this. There is the energy meter over here. This energy meter of the compressor readings we can take. We can note down the initial meter reading. You will find such meters at your homes also. So we can take down the initial readings of this meter. Then you can take down the final reading of the meter. Divide the two, take the difference of the two, and divide it by time. So that meter readings upon time would give you the kilowatt of the compressor. You know that one unit of electricity is 1 kilowatt hour. So 1 kilowatt hour is the unit of electricity. So you can read this, the response of this 1 by 10 kilowatt hours. So accordingly, one can read the meter and one can find out how much kilowatt hour is consumed by this compressor in a given time. And upon the time of the conduction of the test, that kWh upon time in hours, that hours will cancel, and what you get is the kilowatt rating of the compressor. So this is how experimentally one can find the compressor power consumed. Okay, so first thing is you can find the refrigerating effect experimentally by noting down the temperatures of the water, MCP delta T upon time, and one can find the power consumed by the compressor by noting down the readings of the meter which is installed in the setup. Okay, so this is how one finds what is called as the experimental COP. We can also find the COP theoretically, as we have studied in the class, by plotting the cycle on the pressure enthalpy diagram. So for that, you know that we need to note down the suction pressure and the discharge pressure. So suction pressure, look at this. This is the suction pressure. Suction pressure means the evaporator pressure. Look at this kg per centimeter square. So you will find that you can read the kg per centimeter square, which is approximately bars, and you can find the discharge pressure, which is again kg per centimeter square. Again in bars, you can convert it into. These are the gauge pressures. You need to convert it into absolute pressures by adding atmospheric pressure. So this reading, the reading of the suction pressure plus 1.013 bar is equal to the evaporator pressure. This reading, the discharge pressure reading shown by this pressure gauge plus 1.013 bar, that would give us the discharge pressure. So we can note down the suction pressure, we can note down the discharge pressure, plot it on the pressure enthalpy diagram, assume it to be a saturation cycle, read the values of enthalpy H1, H2, H3, H4, and this is how we can find the specific compressor work, which is the enthalpy difference across the compressor, and specific refrigerating effect, which is the enthalpy difference across the refrigerator. So getting that enthalpy will help you to determine the theoretical coefficient of performance of this system. Okay, now note down that we have simply taken the suction pressure and discharge pressure, we have not taken down the temperatures. So why did we do that? Because we had assumed it to be a saturation cycle. But that is not the case. In real life, it is not a saturation cycle. It could be sometimes vapor entering the compressor is slightly superheated, and it's possible that the liquid which is entering the expansion device is subcooled. So how do you know that? So we need to note down the temperatures. Look at this. This is the gauge. This is the indicator, okay, which is connected to the thermocouples, and you can see that it notes down the temperatures. So you can get the actual temperatures after evaporation, right? That is before the suction of the compressor. After compression, that is before the suction or before the condenser. After condensation, that is before the expansion device, and after expansion, that is entry to the evaporator. Okay, so we can note down the salient temperatures T1, T2, T3, T4 by rotating this. Okay, and you can rotate this and note down the actual temperatures. If you know the actual temperatures, if you know the pressure, we can plot the actual cycle on a pressure enthalpy diagram. Okay, the refrigerant which is used over here is R34A, which is tetrafluoroethane. So we need to use the pressure enthalpy diagram of tetrafluoroethane. Don't use it for R12 or for R11. Okay, because the refrigerant being circulated in the setup is R134A, we need to use the pressure enthalpy diagram of R134A. If we are doing the calculations using the tables, the refrigeration tables, we need to refer to the refrigeration tables of R134A. So I guess that this setup is understood. What is the aim of this? Let me just summarize what I have told. The aim of this is to demonstrate the principles of vapor compression refrigeration system. Okay, now how do we demonstrate it? By actually measuring the suction pressure, the discharge pressure, and the temperature. We also determine the experimental COP by finding the refrigerating effect using actual temperature measurements and by using the actual power consumed meter. Okay, so this is a very fun experiment, and when you come over here physically, you will really enjoy the experiment. Our technical expert, VW Jadhav sir, will assist in conducting this assessment, and hopefully we would be in a position to conduct this. Thank you very much. Bye for now.
Okay. So this is the same thing. Why these ads?
Control your home your way
Aha.
with Thv. Thv. Connect your home to your life.
I think it had gone.
Type 2 diabetes can be reversed.
The thought that I was diagnosed with a disease which wouldn't go away for the rest of my life, that was scary.
We are very afraid of that. That word only, diabetic means.
I'm thrilled to let you know that I am free of diabetes and I've stopped taking all my medicines.
My sugar levels have dropped, and
Omkar,
my energy is
there a mouse.
They got better in about 10 to 15 days of time. They come to me and say, Doctor, thank you for referring me to a wonderful program.
Looking back, I think it was one of the best decisions of my life.
Gone. This is one. केला वगैरे याला चालणार कसं ते Okay, fine.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking inside one of these, the thermal expansion valve by Danfoss.
Coming up, where do we find them, what are they used for, and then we'll cut one open and discuss the internal components and how they work. If you want to get the most out of any thermal expansion valve, then you should definitely check out the Thv Superheat Tuner. It's a free mobile app available from Danfoss, who've kindly sponsored this video. You can use it to optimize the energy efficiency of the cooling system in just 15 minutes, which saves money on energy costs. You can download it for free using the link in the video description below. So where do we find the expansion valve? Expansion valves sit between the condenser and the evaporator in a refrigeration cycle. In this model, which is a T2 thermal expansion valve, we have the main body, which is made from brass. On the body, we have the refrigerant inlet at the bottom of the valve, then the refrigerant outlet at the side. And on the other side, we have a cap which can be removed. Under that cap is a screw which is used to manually adjust the superheat. We'll see how that works later on in this video. On the top, we have this large head called the power head. There's also a coil of very thin tubing known as the capillary tube, and there is a large bulb at the end of it known as the sensing bulb. These are all made from stainless steel. The coil is stretched out so that the bulb sits at the exit of the evaporator to sense the superheat. We have previously covered in great detail how thermal expansion valves and electronic expansion valves work, as well as the different types of expansion valves used on chillers. Do check those out.
Hello, am I audible?
Below.
Yes.
Yes, sir.
Valves used for.
Just wait.
Expansion valves control the flow of refrigerant into the evaporator in response to the cooling load. They measure the superheat at the outlet and react to this, increasing or decreasing the amount of refrigerant flowing into the evaporator to try and maintain a constant superheat. This also ensures that the refrigerant is boiling off. It will leave the evaporator as a slightly superheated vapor and prevent liquid refrigerant entering the compressor. Liquids cannot be compressed, so if they enter the compressor, this can cause severe damage and even destroy it. The bulb is filled with a refrigerant which is kept completely separate to the refrigerant in the rest of the system. These two refrigerants never meet or mix, they are always separated. The superheat boils the refrigerant inside the bulb, and as it boils, it creates pressure. The pressure travels along the hollow capillary tube and into the power head. The power head controls the flow of refrigerant, and we'll see inside that later in this video. We place a removable cartridge inside the inlet of the expansion valve. This has an orifice which works with the valve to control the flow of refrigerant. There are different sized ones depending on the cooling capacity and the refrigerant being used. Okay, enough about that. Let's cut it open and look inside. I'll just put the valve into a bench vise to keep it steady while I cut it open. Because of the delicate parts inside, I'm going to use a hacksaw to cut this one open. It does take a little longer, but the angle grinder could rip apart the internals, and I want to be able to show you these parts. Okay, that's the
असं
first
कसं
cut
झालेलं
done.
होतं ते?
Just rotate that in the vise to cut the other side open. Again, I'm just going to use the hacksaw here to cut through it. That's pretty much cut now. I'll just use a chisel to snap the last little bit inside. And there we go. So let's have a closer look.
Okay, am I audible?
Yes, sir.
Let me find. This part is over. Photos are shown. So I have noted down 2 other videos related to related to the theoretical part, which I will be also covering in the class at 3 o'clock. And there is an NPTEL lecture in which it is explained in very good sense. So I will be sharing those links also, YouTube video, which are having, I think, IIT Kharagpur, NPTEL lectures related to REC, in which this vapor compression cycle is explained. So that also I will share, so that before the practical part, you will be theoretically completely clear. Now, what I want you to do is to note down certain readings, or I have to share this. No, if I share it, then it becomes like a assignment, right? So let us do in one sense.
You can share without making it an assignment.
No, then that will be like a attachment. I don't want to do that. Write-ups, then this. Huh. So I will today just give you these readings, and rest of the things we will do on Friday. Friday I will be conducting a lab session. Last week का जो miss हो गया था वो, because I had to cover the theory first, obviously. What I can do over here, I can.
Sir, at
share
what time, sir?
जो भी आप बोलो. मेरा एक एमटेक का लेक्चर होता है, वो छोड़ के.
सर मॉर्निंग में लो सर, ऐसा है तो.
जब भी आपको चाहिए, 9 o'clock, 8 o'clock, 7 o'clock in the morning, I'm ready. Can you see this table?
Yes, sir.
Yes, sir.
So everyone just make it in your notebook. And then I will tell you the readings. So time required to fill 1 liter of water, and means 1 liter and time. So I will get m dot. Then evaporator pressure I will tell you, condenser pressure I will tell you, TW1, that is the room temperature, TW2, which is the cold temperature, and time for 10 revolutions of energy meter. So पहले इसको बना लो, then I will give you the readings, and all further discussion after the theory lecture only. Otherwise you won't understand. Experimental part you can understand very easily. I have also explained, and 2 other professors from 2 other videos, they also explained. So that part you can do. But comparison with the pH, that you cannot do at this moment, because I have not taught you pH. So let me first cover that in theory. Then we will get back on Friday for the pH chart. So is the table done in your notebook?
Yes, sir.
Okay. Just take a white paper, notebook, blank page, write down about this table, make this table, and then I will give you the readings. Should I stop sharing the screen? Have you made the table or still drawing it?
Just a second, sir.
Done?
Yes, sir.
Okay, so now I will give you the readings. Where is that page? Yes. So we have 3 readings over here. So we can make 3 groups. How much is the strength of the class? 80?
Yes, sir. 80.
So let us make the group of 25, 25 and remaining. Everybody need not do all 3 calculations, right? So first 25 will do the calculation for the last reading, second 25 for the middle reading, and remaining people for the first reading, reverse way. And then
Yes, sir, fine,
exchange.
sir.
Okay. So write down the first reading. The time required to fill 1 liter of water, write down 9 seconds.
This is for which group?
As I said, first reading for the last group, no?
Okay.
Means last kitna aa jayega? 25, 25, 51 onwards. That is the last group. Okay, so 9 seconds. Then your evaporator pressure in MPa, megapascal. So write it down as 0.446. 0.4 MPa means 4 bar, correct? 10 raised to 5 and 10 raised to 6.
Yes, sir.
So 0.446 MPa, that is evaporator pressure. Condenser pressure will be 1.48 MPa. So this is 14.8 bar. Why I have taken in MPa? Because our charts are in MPa. Look at the chart, ASHRAE charts. Everything is in MPa. That is why I have converted into MPa. Fine. TW1 is 30 degrees Celsius for all 3 groups because that is a common one. Okay. And TW2 is 24 degrees Celsius. Fine. Last reading, that is time for 10 revolutions, is 114. 114. 14 seconds. Is the first group done?
So,
First means last group. Yes.
so could you please repeat the time required to fill 1 liter
I
of
will
liquid?
repeat all the readings. 9 seconds as the time required to fill 1 liter. Evaporator pressure 0.446. Condenser pressure 1.48. TW1 is 30 degrees Celsius 30. TW2 is 24 degrees Celsius. And time for 10 revolutions of energy meter is 114.
Thank you, sir.
Cross check. Okay. Should I tell the second group readings? Readings for the second group. So this will
Yes, sir.
be 26 to 50. Okay. Write down. Time required to fill 1 liter of water is 14 seconds. Evaporator pressure is 0.425 MPa. Condenser pressure is 1.441 MPa. Inlet temperature 30, I already told. TW2 exit temperature is 22 degrees Celsius. And time for 10 revolutions is 118 seconds. I repeat, time required for 1 liter of water 14 seconds. Evaporator pressure 0.425 MPa. Condenser pressure 1.441 MPa. TW1 30 constant. TW2 22. And time for 10 revolutions of energy meter 118. Clear?
Yes, sir. Yes.
Okay. And now the third reading, that means first group, that is roll number 1 to 25. Okay, write down. Time required for 1 liter of water, 20 seconds. Evaporator pressure is 0.418 MPa. Condenser pressure is 1.44 MPa. TW1 is 30 constant. TW2 is 20. And last part, time for 10 revolutions of energy meter is 114 seconds. I repeat, time required for 1 liter of water, 20 seconds. Evaporator pressure 0.418 MPa. Condenser pressure 1.44 MPa. TW1 30 degrees Celsius constant. TW2 20 degrees Celsius, and time for 10 revolutions is 114 seconds. All three groups have taken 3 sets, individual sets. Correct?
Yes, sir. Yes, sir.
Okay, fine. So we'll stop over here for the time being, because, or otherwise you can just do the calculation for MCP delta T. That is not something very difficult, correct? So all 3 batches you do your individual MCP delta T calculation. M dot, that is 1 liter by, let's say, 9 seconds, 1 kg by 9 seconds, or 1 kg by 14 seconds. CP is 4.1868 or 4.187. And delta T, you know, 30 minus 24, 30 minus 22, 30 minus 20. Done. So you get the reading in watt or kilowatt, whatever it is. .1868 means kg. So you will get the final answer in kilowatt. So how much it is? Let's say first group. Yes, how much is your Q absorbed? Kilowatts.
Sir, 2.78 kilowatts.
2.7. It is the first group or second group or third group?
Sir, the first reading, last group.
First reading, last group. Okay. 2.78. Okay. Second group, second reading.
$2.39, sir.
2.3?
9.
39. Okay. Whatever it is. Fine. And third group?
2.1 approx. 2.0935.
09. Okay. 2.1. Whatever. Fine. So you are done with Q absorb. Now about the work done. So for that, write down a formula. Work done is equal to 12 into number of revolutions of the energy meter. So that is capital N, divided by time required by the energy meter. So our number of revolutions are 10. Correct? So it would be 12 into 10 divided by time. Time you have noted. And this whole thing is to be multiplied by the efficiency of the compressor. So efficiency of the compressor is to be taken as 0.7, 70%. Okay, so it would be 120 divided by T, that is time which I have measured, into 0.7. 120 into 0.7 मतलब कितना हो गया? 84. 84 divided by T. Are you getting it? 12 into 10 into 0.7. So that is 84, 12 into 7, 84 divided by T. And every group is having your own T values. Last column. 114, 118, 114, whatever. So that is your input. That is your compressor work. So how much it is? It is more or less same only, na? 114, 118, 114. So more or less same only. So how much you are getting it?
9.33.
Huh? What is this?
Kilowatt. Sorry, sorry, I'm so sorry. Joules. Kilojoules.
Why you are getting kilojoules? It would be directly in kilowatt. Per unit time.
0.737.
0.7. Okay.
0.711.
Whatever it is. 0.71, 0.73, whatever it is. हे 9 point वाले कोण होते? काय चुकलं बाबा? 12 into 10 into 0.7 divided by small t. Last column. 114 or 118 or whatever it is. So it is 84 divided by something. And 84 divided by 114, how can it be 9?
हाँ सर मी एफिशिएंसी मध्ये चुकवलं.
कत्ती.
सर ये जो कंप्रेसर एफिशिएंसी है, इसको हम न्यूमरेटर में मल्टीप्लाई क्यों कर रहे हैं? मतलब
Energy meter constant जो है ना 12, that is designed in such a way that if it is 100%, then that is the constant. So we have to go for 70% of that.
Oh, अच्छा. Okay.
The energy meter constant value 12, which I have given to you, that is for 100% efficient compression. Ours is 70%, so I have to take 12 into 0.7.
सर सो एफिशिएंसी कम हो रहा है तो हमें कंप्रेसर को इनपुट कम देना पड़ रहा है, ऐसा मतलब है कुछ?
कम देना पड़ रहा है मतलब वो कम ले रहा है.
तो कम ले रहा है तो सर ज्यादा एफिशिएंट सिस्टम हुआ ना सर वो?
नहीं, उसको कंप्रेस करने के लिए ज्यादा वर्क चाहिए, but it is not capable of taking that much work. It itself is 70% efficient only.
अच्छा, तो सर ये लाइक इज अ वॉल्यूमेट्रिक एफिशिएंसी टाइप है.
हाँ.
ओके.
Fine. So now you got Q absorbed individual. Correct? Whatever 2.8, 2.39, 2.09 जो भी था. And the work done 0.73, 0.71, etc., etc. So you can tell me the COP experiment. So how much it is?
2.841.
2.841. Which group is this? Last one?
Yes,
or
sir.
first one? Okay,
Third
so that
one.
third. Okay, fine. So that means it is the least COP, na? Because your Q absorbed is lower.
Yes, sir.
Fine. Then any other group?
3.356 sir.
3.356. So this must be the highest one or the intermediate. How much is your Q absorbed?
Q absorbed is 2.39 sir.
हाँ, तो second group इसका मतलब ठीक है. So 3.36. Okay. So 2.84, 3.36. So first group should give the higher reading.
2.84 only, sir.
Huh?
2.84.
2.84 are which group?
The first group.
First group?
So
Means
first
you absorbed 2.8.
Yes, sir. 2.841 was first group. The third reading.
That is third reading, na?
Sir,
Q absorbed is 2.1.
Srikanth also told for the first group, that is the third reading.
Correct. Q absorbed is 2.1. उसका ही बोल रहे हो ना, COP. That is 2.84 something.
Yes, sir. Yes.
हाँ. Then someone said about 2.4 Q absorb, second group. That he said to 3.36. That is okay. What about Q absorb 2.8? First reading.
So 3.782.
3.78. Fine. So that is in the decreasing order. 3.78, 3.36, and 2.84. Correct?
Yes, sir.
Okay. So what is changing? Your Q absorb changing. Q absorb decreasing. Work done almost constant. So that is why COP decreasing. Do you agree?
Yes, sir.
Fine. So we'll stop over here because unless and otherwise we cover up with the pH chart. उसके बाद ही बाकी का discussion हो सकता है. So at 3 o'clock we will meet again in the theory lecture. I will cover for the pH part, pH chart, and on Friday we will have maybe 1 hour discussion only for this thing. Fine. Any doubt to anyone up to this part? We covered only for the experimental part, no theoretical. वो बाद में. Okay. In the meantime, if I get the pump started, I will show you the live setup also, or maybe in the next week, whenever possible.
Okay, sir. Thank you, sir.
Fine. Okay. So should I end the meet? Nobody having
Yes,
any
sir.
doubt?
Thank you, sir.
Yes, sir.
Sure. Thank you.